Hello. Today we are starting Chapter 4, Quadratic Equations and Functions. And Lesson 4.1 is about quadratics and transformations. So your objective today is that you will be able to identify and graph quadratic functions. The key concept here is the parent quadratic function. We have parent functions for a bunch of different things. We have parent functions for linear, which is simply y equals x. We have parent functions for absolute value, which is y equals the absolute value of x. We also have a parent function now for the graph of a quadratic, and this is y equals x squared. And that is the graph of this parabola that's shown. So we're going to learn about something called the axis of symmetry and the vertex. Now the vertex of our parent function here, that is where the graph switches directions, is at 0, 0. And then the axis of symmetry goes through that vertex point. So our axis of symmetry, something interesting to notice here, is always the x value of our vertex. We also have something called a maximum point and a minimum point. Each quadratic will have either a maximum or a minimum. So our maximum would be if the graph was this way. It's the highest point here. This graph has a minimum because it is the lowest point. So our minimum of this specific graph is our y value of our vertex. So this graph has a minimum of 0. Okay, those are just good things to know and will be on your Math Excels. So now we are going to use a table to graph these two different quadratic equations. And then how do they compare to the graph of our parent function? So our parent function, you'll notice, I'm just going to copy it down here, starts at 0, 0. Our next point is at 1, 1, and then the point after that is at 2, 4. You'll notice if I made a table for the parent function, ooh, that's not very good. Parent function would be xy I always start by putting my vertex point in the middle of my table, and then it would be, say, -1, -2, 1 and 2. We plug in those values here. -2 squared is 4, -1 squared is 1, 1 squared is 1, and 2 squared is 2. So I just fill them in, and then I plotted those points. Okay? Now, we also have an axis of symmetry here. That axis of symmetry tells us that this graph is symmetric on either side of it. Now I'm going to go ahead and make a table with regards to y equals, or f of x equals 1/2 x squared. So we'll learn in a little bit how to find the vertex of these sort of quadratic functions, but for now I'm going to say that the vertex, I know for sure, is 0, 0 for this one as well. So our vertex is there, so then I'm going to do numbers on either side of it for my x values. And then I plug them in. So I'm going to use some workspace over here, y equals 1/2, parenthesis. I'm going to do this guy here, instead of the negative version, 1 squared. I know 1 squared is 1 times 1/2, so this answer is 1/2. Gonna replace this with a 2. 2 squared I know is 4 times 1/2 is equal to 2. Okay, so from here, I know that there is an axis of symmetry through my vertex, which means I don't need to do math to find the y values for -1 and -2. I can go ahead and plot these, and then I just reflect it across, and then draw my graph. Notice how I do not just draw a straight line in. This is not absolute value. It is quadratic. They're kind of curvy, like a U shape. And that is the graph of y equals 1/2 x squared. We also need to find the graph of y equals -4x squared. I'm going to do a little table down here again. But you know what? Before I move on, I'm going to copy these guys over because they are the same. There we go. So do the little table. Once again, I know I'll teach you in just a minute how we find that, but I know my vertex is 0, 0, so I put that in the middle. Choose numbers close by. Sometimes we want to be smart about what numbers we choose and choose different ones, but for now these ones work. And then we just plug these in. So -4 times 1 squared. Well, 1 squared is just 1, so -4 times 1 is -4. That means because this is symmetric about its axis of symmetry, that -1, -4 is also a point. And then we plug 2 in here. So we have 2 squared is 4, and 4 times -4 is -16. Now this will be way off our graph. We'll do our best to graph it so that way you can see. Down here somewhere. And then I can graph these out. And those are the graphs of my 2 equations. Now it does ask, how do these compare to the parent function? Well, I would say the vertex, it stays the same. That does not change. But for the graph with the 1/2 times x squared, that gets compressed. It gets squished down towards the x-axis. So it's compressed a little bit, while the one that is -4x squared, it flips over the x-axis, becomes negative, a sad typeface, and then it gets stretched, pulled up and narrower. So if you can recall from the absolute value section that we did problems similar to these, we have the reflection. If what we are multiplying it by is negative, it's a sad face. If it's positive, it's a happy face. The stretch, if it's greater than 1, it stretches it, makes it narrower. And if it's between 0 and 1, so a fraction, it makes the graph slightly wider. Now, also, let's take a look. We have our axis of symmetry line for all of these. Is x equals 0. It's that point of our vertex. These are all 0, 0. So the point of our vertex is 0, which means the axis of symmetry is 0. And then our, say for the pink one, our maximum point is 0 because our y value is also 0. We'll do one where they're not the same so that way you can see. Okay? Now, we have an equation for this. Y equals a, parenthesis, x minus h squared plus k. This is our form that we are using currently. Similarly to our absolute value lesson, we have the opposite of h comma k is our vertex. So we can use this information to then solve. So we've already figured out what a does. That guy's up here. We will recall what h and k do. So k, we know this is a k because it is not inside the parentheses, while this -4 is inside the parentheses with the x, so it is an h value. So we can go ahead and find our vertexes for each of these. If our vertex is the opposite of h, which doesn't even show up in this one, 0, h is 0, and then k stays the same, -5. So our vertex is over 0 down -5. Then from here, nothing is multiplying this guy. That means we don't have a reflection, we don't have a stretch or compression. If we were to have that, I suggest writing out a table and then solving each individual number using the table, and this as your center value, like we had 0, 0 for each of these. But because there is not an a value, we can just go ahead and pretend that this is our new origin, and then graph the parent function x squared from there. You could also do a table on this, but you don't have to. So I had written out the graph of the table of the parent function. If I use this table, starting from this new origin, in quotation marks, because it's not really the new origin, I will graph on my axis of symmetry one side and then reflect it across. From this point, I'll go over 1, up 1. Then from this point again, I'll go over 2, up 4. Then I can reflect these across. And I have graphed this line. Or sorry, it's not a line, it's a quadratic. I have graphed my quadratic now based on my original parent function. It's just moved vertexes, not shapes. Now, if I want to say my axis of symmetry, that would be this value right here, so x equals 0. And then my, in this case, minimum point, because it is the lowest point on the graph, is actually just my y value of my vertex. The minimum is -5. So if we wanted the domain, that is all real numbers. It will extend forever, all the x's, forever and ever. If we wanted the range is the y values. It would be y It'd be real numbers of the y values greater than or equal to -5. Because it starts here and it goes upwards forever and ever. So we won't do those 4 things on the next few, but you get the idea. On this guy, this next problem, we have an h value, which means we need to take the opposite of h for the vertex. So +4, 0 is our vertex. So we go over +4, up 0. Then once again, I treat this as my new origin in parentheses. The origin's still really here, but I can graph my parent function based on the original from that new vertex. So there is half of my quadratic graph. I need to reflect this over and then draw in nice curved sides, don't make them straight, to draw in my graph. Now notice I did say we weren't going to do all of these, but I guess we'll do one more problem of them. Copy this over. Our axis of symmetry has now moved. So has our minimum. So our axis of symmetry is now our x value 4. X equals 4 is the equation of this line that we have drawn. Our minimum is now, the lowest point is 0, this y value. Our domain has stayed the same. It still will cover all x values, but our range has changed. We now have all real numbers greater than or equal to 0. Notice these guys are the same for both of these problems. Okay? Two more real quick. So I have to find my vertex, 0, 3 in this case. I go over 0, up 3. Once again, there's nothing multiplying this x squared, so I can just do that sort of parent function. Reflect across my axis of symmetry. And draw it in. If you'd like, you can take the time to find those other things, but that's just the graph. And lastly, once again, we need to find my vertex. So I will have the opposite of h, so -1, 0 as my vertex. So I go over -1, up 0, and then I graph from there. Now you can make a table to solve these, plug in and find it. Make sure you follow the order of operations. You also can have h and k values happening at the same time. So you could have a graph up here doing this thing. Doesn't have to stay on one of the axes, just these examples did. All right, that does it for today. Have a great afternoon.